maybe the positions of these down around so you can package yourself so you don't whack into the base and you can actually pull down with enough pulling force to score a 2 times multiplier. You can't see here, but if you look, this base was made with a slot here so she could move her base platform relative to her arm. So she did all that, and then she went into the phase of her most critical module. So what do you think the most critical module of this system might be? Yeah. Yeah, a way to extend up, because here's how she would look in the starting box. She can't go above 12 inches. So she needs a way to not only extend up, but also a way to exert enough force to pull that 30 newtons down, right? Or lift a 30 Newton robot up, right? So she started thinking about most critical module mechanisms. So, she thought first of a lead screw idea, and then a winch idea, and a rack and pinion idea. She again made this pew chart and compared these to each other. She realized, a winch really only works in one direction. You can't push on a rope with a winch. And so she calculated this all out and realized that, boy, a rack and pinion seems like a viable option. Then she also did some analysis about what motor could be good. So one of the motors you have down there is a big torquey motor called a VS11. So she looked at the operating voltage, she looked at how fast it rotates, she looked at the stall torque, and just like I drew with the hybrid supercars, she drew a torque speed curve and realized that if she wants to lift this down as fast as possible, she should make her drivetrain such that it's operating at the max power, right? So then she started drawing some schematics of this gear train and the gear sizes and the tooth sizes. See, there's a 24 tooth and 36 tooth gear down for the pinion. She did, may the torque be with her right here. Look at this torque force diagram. Yep, figuring out the radius of the gear and how much force she would actually exert, and figuring out that she can apply enough kilogram force to actually pull this thing down. And then she made some sketches of a most critical module, just a simple rack and pinion system. And just like a cooking show, if I go over to my trunk, I have a rack and pinion system. So this would be an example of an appropriate most critical module where you've had to think about your motor choice, how much force it can output, how much throw the rack and pinion has. So let's plug this thing in and see if it works. I hope my battery's still on. I unplugged it. Or I didn't unplug it. Okay, we'll go on channel 1. And we'll turn this guy on. Let's see. All right. So, here's the most critical module set up. You can see this slides really well. She thought about her bearings. And we could pretend like we extend this up. I'm making like I'm a robot. Extend this up, hook on, and will it pull it down? Whoops. You can see some dexterity is important here. Okay, so if I hold this in place, see, this has plenty of torque to pull that down. So that's a really important test. She knows that motor is now actually torquey enough to do this operation. So she did all that work, and then for the last phase, if I go back over to my cooking show oven, she came up with this guy. And this is her actual robot. With heavy weights on the bottom. Let's get a battery on here. And let's see if this sucker works. So this is the actual robot that she used in the competition to get 4th place, which is quite good. There's 165 of you in the class, so it's damn good. All right, so let's see if I can do it. Whoop. Okay, so she had to drive over, and this is where practice matters. She had to extend this system. She actually realized that she wanted to use a combo rack and pinion in capstan drive. You're going to learn about capstans from Professor Kim. Whoop, I think I have a slipping tire, but I can still get there. Whoop. Can I do it? You can see, this is what it's like in the competition. Oh. Bam, look at that. The thing did a pull-up. Let's give Emma a round of applause. So, you know, she did an excellent job designing this whole thing. This is her other robot, her quick little Schmiegel robot, and this could zoom up and down the slope super fast. This is actually a catcher for a rail that was in the middle of the slope, the steep slope, so she didn't flip over backwards. But she did awesome. And I know I gave you kind of the cooking show example of all of that, but I have Emma's actual notebook here. This was really based on a true story. Like, if you look through here, she has all these beautiful, like, look at all these prototypes of the rack and pinion system, her CAD models. Earlier on, she does, look at all these calculations. Like, Emma was an awesome, awesome student in this course. What's that? It's legible. It's legible, too. She's dating everything. Look at all this. Oh, look at this strategy. She's got the sketch out of doing the loops of the upper slope versus lower slope and how she's going to score points. Here's the point totals. Like, this all really happened. Isn't that awesome? Yeah. So, you guys can do the same thing. All right. So anyway, going back to this and going back to the competition and thinking about your competition, I want you guys to be considering, you know, what different scoring strategies could you use? What different actions could your robots use to score points? How much time is it going to require to do those actions? Drive a Mini-Me. Time how fast it goes from point A to point B. Add some buffer for control, right? They're not fast robots. But we do have some awesome, powerful motors this year to make them fast robots. Think about physical movements to complete tasks. Like prototypes like this can teach you a lot about, okay, I have to drive in like this and pull like that, and give you ideas of degrees of freedom and drivability and all that good stuff. And then do some power, energy, torque, force, blah, blah, blah calculations. You guys know all that from 801, and we're going to really, really stress that. Now, I want you to consider your design constraints and actually list these in your notebook. So things like, you can't control what mechanical parts you can use. That's dictated by the rules. You can't control how much power you can output by your motors, because you're limited to motors. You can't control the surface features and friction of the game board. You have to work around that. You can't control how much time's in a competition. 2 minutes, 90 seconds in manual control. But the converse of design constraints are design freedoms. And I want you guys to think about explicitly aspects of the competition that you can use to your advantage. So things like materials. You know, go down, and this is what your lab's going to be this week, go down into the lab and feel all these materials and rub them together and like try to bend them and, you know, really get a sense of these and be like, oh man, this sucks as a bearing. It galls, it stinks, but ooh, I could use Delrin and this is like really smooth and low friction. You know, that's going to give you insight into how to make really nice systems. Actually, Emma has a really nice laser cut bearing guide of a low friction plastic in there. You should check that out. Oh, I lost my thing. So yeah, think about all these things that you can exploit to your advantage. Geometry, right? So like, could an angle bracket make a good motor mount? Does that just naturally lend itself to a motor mount? Does sheet metal help you out by being very easy to manufacture, and you can just cut it out on the bandsaw, punch some holes, and then bam, you get a part of your robot already made. Think about those things you can use to your advantage. How can you store energy? How many batteries do you have? Can you store energy in rubber bands or springs or whatever, right? Actually list all of these down, because these will catalyze new ideas for your robot. Okay, so just to wrap up, I want all of you to check out on the Stellar site, or sorry, on this link, this design process video that Professor Fry did a number of years ago, which will also walk you, you're not leaving yet, Dr. Wendell has to talk about something. So check that out, and then if you want to see a bigger history of 007, here's the link. And just a few announcements. Please read the course info and policies sheet and the timeline of the class. We're going to post the rules pretty soon, so you can start checking those out. Monday's lab section, again, has to come to other labs this week. Milestone 1 will be assigned in your lab this week, due next week, but it's already up on Stellar if you want to check it out. Written homework 1 will be assigned on Sunday and will be put on Stellar. I'll send out an announcement for that. And now I'll hand it over to Dr. Wendell to talk about lab sections.
I need a mic though.
All right.
It might not be the right one. It's not the right one. First of all, we have 2 mics.
We have two mics because we film all the lectures too, so you can refer back and watch a video.
Yes, so talking about Stellar. Stellar is the primary mode of communication and the #1 way that we get information to you, so make sure you have access to Stellar. Now, Stellar is also where your lab section assignments are. You don't care what the registrar imagines in their happy little minds. Stellar is the lab section assignments for this class. So, if you pre-registered and received emails from me telling you to select your lab section, some of you were able to do that, some of you are on the waiting list, and I'm going to go over how we're going to handle the waiting list and all the sections. I ask that you please hang out until I finish explaining all of it, and then some of you won't have anything to do and get up and go, but please don't get up and start moving because then everyone else can't hear me. So, if you selected your section on Stellar, and it still works in your schedule, and you are happy with it, you are all good. Unless you want to get like massive karma points forever, and somehow you think you might be able to do the Wednesday morning lab section. That is historically our least enrolled section, but it has phenomenal faculty, professor, people, instructors. So if you would be willing to switch to allow someone else into this class, you can write that on your form, and you can say, please don't move me unless absolutely necessary, but I'm willing to be an awesome person, and put that on the form and turn it in. Otherwise, you can just stay in the section you're in. If you do not show up to the section that you signed up for, and lab start today, your spot will be given away. We have about 50 people that are unassigned, so we're going to try to find everybody's spots, but that means that we're going to fill up any spots that open up. Now, if you do not get an assignment, you do not select the last section you want to full, whatever, please fill out this form. Fill it out with as much information as possible, either processed by hand by me and the TAs immediately following this class and for the rest of tonight. So you can write us notes like, I have this section, but like this class might switch, or can you please maybe give me, this lab section, but I'm willing to take these other ones if it'll get me in the class. So please fill that out on the form. And also, if you are waitlisted, if you received an email saying you are specifically waitlisted, or if you did not pre-register, that means you are also waitlisted, please fill out this form, because this is then how I'll figure out the waitlist for each of the individual lab sections. Any questions about that? Yes?
When do you need these forms by?
I need these forms by the end of class, which is in 7 minutes. Yes?
So if we're unregistered and we go to like the lab section today and there are these spots?
There are no spots today.
Okay.
Please do not show up for random lab sections because it's a machine shop class, so we can't just have like infinite numbers of people in the shop. So please don't show up to a lab unless you are told specifically you have a spot in that lab. The only exception to that is the Monday sections, as Professor Wicker said, so you have to